Good afternoon, Year 8. This is our first real remote learning lesson this time. So we're learning about energy efficiency today. Your learning intentions are to learn about energy efficient, and that means you're going to be able to tell the difference between used and wasted energy and also be able to do some calculations. So you're going to need to have your CAS handy. So what I want you to do is obviously watch this video and then do part of lesson 1.3. Where I want you to stop is at the subtitle called Comparing Energy Efficiency of Cars. Okay, let's start with a little terminology. You've got three terms that you'll definitely need to know today: energy efficiency, useful energy, and wasted energy. Energy efficiency, it measures how much of the total energy that was supplied is actually used, how much of it is useful energy. Useful energy is energy that's been transformed from one form into the form that we actually want. So for example, in a kettle, we're taking electric energy, and if it's useful, we'll transform it into heat energy in the water. And finally, waste energy is energy that is put to the machine or the object, but it's not used as intended. It's been turned into a form that's different to the one that we want. Okay, so we'll use this diagram a Sankey diagram to help us with our understanding of those three terms. So we've got four types of energy in this. We've got chemical, kinetic, sound, and heat. What's going on in this diagram is we've got the chemical energy that's stored in our fingers from our food, the sugar that we eat. This gets turned into kinetic energies to make our fingers move. That in turn makes the strings move, and the movement of the string makes sound. Now, it's each step a little bit of energy is lost to heat. So that means that these red ones where the arrow points down and sort of disappears and doesn't continue on, that's the wasted energy. Okay, so that's the wasted energy. I've circled that in yellow for you. This means that all the other energy up the top here is useful energy. Okay, so the green is useful energy, the yellow is wasted energy. Now, the energy efficiency, it's basically we're comparing the size of these arrows to the size of the arrows that are lost. And we actually do a mathematical equation to figure this out. Let's continue. Okay, so what I want you to go to do now is just under that diagram in style, you have a few multiple choice. So if you can pause this video and take a couple of minutes to have a go at the multiple choice, please. Okay, so the second thing you need to be able to do today is actually calculate energy efficiency. So we have another Sankey diagram here today. You can see the arrows going in. So we've obviously got the total energy, we've got useful energy, and we've got wasted energy down the bottom. Underneath that, you should be able to see a calculation where it says efficiency equals useful energy divided by the total energy, and it shortens it to equals A divided by B times 100, where A is the useful energy and B is the total energy. So let's look at an example. All right, so the first example I'll talk through is a solar panel. So let's pretend this solar panel can create 300 joules of energy from 1500 joules of sunlight, remembering that joules is the unit that we're going to measure energy in. Let's have a look at that. So let's let A equal, and remember this is the useful energy, so the useful energy is the joules of electricity, 300 joules. So that's 300. So A equals 300 joules. It's a capital J. And we're going to let B equal 1500 joules. So now that we've established our variables, let's put it in the equation. Remembering that the equation is A divided by B times 100. So we're going to have to substitute A for 300 and B for 1500. So using your math skills, which I'm sure you guys have abundance of, we can cross out all these zeros on the top and bottom. So we're essentially doing 3 divided by 15. Now 3 is 1/5 of 15, or 0.2%. So we're going to have 0.2 times 100 is going to give us 20%, energy efficient. So that's not incredibly efficient, and generally solar panels aren't incredibly efficient, but we are getting better and better at making more and more efficient ones. Okay, so what I'd like you to do now is pause this video and have a go at the couple of questions, question 5, question 6, and have a go at question 7 as well on sector. I will talk through the answers in just a second. After you've done the questions, you can watch this next portion. Okay, so for question 5, you've got quite a lot of information. You've got an electric drill converting 200 joules of energy, 2,000 into 400 in the kinetic energy in the turning of the drill, 800 in the noise that the drill makes, and another 800 of heat. So we've got to work out the energy efficiency of the drill. So the first thing we need to do is figure out which one's the useful energy and which two are the wasted energy. And the reason we use a drill is to turn the screw into the wall or wherever we want to put it. So we want kinetic energy, and that's the 400 joules. So we're going to take 400 joules, we're going to divide it by 2,000 and multiply it by 100. Okay, so we've got our wasted energy here. Our yellow highlighted stuff is our useful energy, and there's our total energy. So this one's going to be A, and over here is going to be B. So we're going to do A divided by B, so 400 divided by 2,000 times 100. You can just plug it into the calculator, but when you plug it into the calculator, don't forget, because you've got 2 zeros up here, and cross out 2 zeros down here. So 4 divided by 20 is 20% again. It's funny, both of them ended up the same. All right, so that's the answer to question 5. Okay, so this is for question 6. We've got John, who likes cooking, is looking for an electric beater. He's considering 2 models and has found the following data for each. So you've got model A converts every 1,000, and I might just grab a highlighter to help me out here. Every 1,000 of electrical energy into 600 of kinetic energy. Now, in electric beater, the kinetic energy is the useful energy again, whereas the heat and sound are wasted. If we look at model B, we've got 1,500 joules, and 800 of that gets converted to the useful energy. Which one is more efficient? Show your calculations. So in both these cases, I'm going to use these 2 values as A and these 2 values as B. So let's set that up for model A. A equals 600 joules, B equals 1,000. So we're going 600 over 1,000 times 100. We're going to cross out those because we've got 2 zeros and 2 zeros. We end up at 6 over 10, which is 0.6, or 60%. For model B, we're going to let A equal 800, so that goes on the top, and 1,500 goes on the bottom, and we're going to multiply that by 100. You can just do 8 divided by 15 times 100 into your calculator, and you should get 53%. So when you convert those 2 values, you can see that 60% is higher than 53%. So that means that model A is more efficient. So make sure you write that in your answer as well. Okay, model A equals more efficient. Okay, the last question has you looking at this chart of light globes. We can see you've got over here energy consumption up the top, and you've got 20, 40, 60, 80, 100, and they're measuring this in watts. And you can see this is the incandescent globe, which is your old-fashioned light globe that you probably don't see anymore much. You've got halogen, which you might use here and there. You've got low voltage halogen. We've got fluorescent, another fluorescent, but this is tube this time, and the LEDs, which a lot of houses are getting fitted with LED lights now because they are so efficient. And you can see that by how tiny the green bar is, whereas the old-fashioned light globes from the 90s and 80s from the last century were quite high. Right, so the question wants you to compare these two particular light globes, and we can see that the incandescent globe is 100 watts versus the compact fluorescent, and if we read across that little black line, it lines up to 20 watts. Okay, if you think of it, and you divide one by the other, 20 divided by 100 is 1/5. So that means that the compact fluorescent globe uses 1/5 of the energy of the incandescent globe, or 20%. The next thing on sector gets us to compare the efficiency of cars. I don't want you to do that today. We're going to do that on Thursday instead. Instead, just to reiterate everything that we've looked at today, we have learnt how to what wasted energy looks like. Okay, and it's the arrows that come off the bottom in a Sankey diagram. What useful energy looks like, and the fact that it is, you can see it going through forward on the Sankey diagram. We've also learned how to use this formula, where useful energy is divided by the total energy available times 100, and that gives you the efficiency of the object that you're using or talking about. All right, message me if you're having any troubles. Other than that, good luck.